right, gang. We know about rotational motion. We know the outside goes faster than the inside. And now we're going to talk about the counterpart to force. We're going to talk about torque. And what I usually have when I do this is I have a piece of wood much bigger than this. I hold it like this, and everyone sees it topples over. And if you put it like this, of course it doesn't if it's supported. And we talk about support force. And you can read the book. It's a lot about that. We'll have something like turns out that the center of mass of that object, and I'm going to skip all that about center of mass right now. The center of that mass of this object will be outside, say right about here, which means that old Mother Earth is pulling down on this object as if all the mass were there. And it rotates about this point here. And so I can put a little imaginary fulcrum, a triangular support. Seesaws ride on fulcrums. And there's a little imaginary fulcrum there, and this rotates about that fulcrum because this force twists the object. We can call it a twisting force, or more properly, we'll call it a torque. So a torque is a force which is off kilter, or an off-center force, or a force that will twist, or a force that has a lever arm. And the torque would be, by definition, some force times some lever arm. Between the line of action of the force and the point of rotation, the shortest distance is this. And that's your lever arm. And when you have a force acting through a lever arm, you'll get a rotation. Just as forces produce accelerations, torques produce angular acceleration. And this thing will rotate down. So that's a torque. We talked about the bus going across the bridge. Let's look at that. Here's the bus here. Center of gravity's here, huh? Where are the support forces?
Right at the wheels.
Ah, one here and one here. And how will these two support forces compare to the weight of the bus? Should we check your neighbor for that? How many say same, same? How many people don't say same, same? Stand up. Excellent. Okay, so we know that these are the same. Any torque here? Well, about the center of mass, this tends to produce a torque like that. Oh, but this produces a torque like that. So the bus doesn't rotate. Now it leaves now it's like that. What happens to the support force?
Ain't there anymore.
Goes away. No more. Now what do we have? Do we have a net torque? Yeah. About here, it's a torque rotating it down. About the center of mass, rotating it up this way. So what does your bus do? You know, what did we see in the movie? The Hollywood version was exactly the opposite. Okay? And this answers the question why it is that when a truck goes off a cliff, that it always noses downward instead of the other way. You can see what happens. Right away you have a torque. And so long that from the time it goes from here to here, that torque is da-da-da-da-da, and the thing is going to rotate. And there's a delightful book written about why is it that the toast always falls jelly side down. And what happens? It slides off the edge. Center of gravity's here. What happens? You get a piece of toast. Here's a piece of toast starting to slide off. So far, no rotation. Center of gravity's here, yeah? Now it slides further and further off. What happens? Pretty soon it's like this. Whoop, center of gravity's here. What do we got, gang? Begins with a T, rhymes with dork.
Torque.
Torque, okay. Get a torque. What's a torque produce? Rotation, okay. So the toast starts to rotate. So people wonder, why was it that when the toast slides off the table, it rotates? And you guys know. Torque. The torque. And now it's going to just... And if the table's high enough, it'll be enough to flip upside down. And the same over here, too. So the Hollywood version of that movie, Speed, completely opposite. What I like to do at this point is challenge people to stand against a wall and assume that L-shape configuration, touch their toes, and come back up. And you'll find they can't do that unless they do as Dave Vasquez did that time. And Dave Vasquez used long ski boots, extra long ski boots. See, the bit is this. You're standing against a wall. I'm giving the punchline away, but when you go to touch your toes, your center of gravity assumes, say, over here. It's the same thing. Pull. Here's your greatest distance. So what do you got? You get a rotation because you get a torque, and over you go. Now, if a person wore skis, no problem, because they'd have a support base here. Well, what David did is he came in wearing ski boots that were just about like this. And his ski boots extended right out there. They weren't curved at the over here, right flat right there. And David was able to do it, and as I said before, got his A. And that's why I increased that. Do you guys know why a ball rolls down a hill? Gravity. Well, I don't have a ball here, but I got a, my hill is an inclined plane, and I've got a can, okay? And a can is like a ball, yeah? And it turns out when I let the can go, which way is it going to go? Put this over here to catch it. And when I let it go, it just, of course, this would be better. Whoops. Well coordinated, gang. And of course it goes this way.
Anti-gravity.
And that is because of anti-gravity, that's right. And then you can humba, 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 humba. And of course we have it like this. Yeah, a trick. There's always a trick. And it's not even a magnet. Okay. Tape, just as sticky. But in answering the question why a ball rolls down a hill, we could say a ball has its center of gravity ordinarily, or a tin can ordinarily in the center. And there's a force there. But your point of contact is over here as if you had a fulcrum. And what do we have right in here, gang? What's this? That's the lever arm. So a force times the lever arm produces a rotation. In this particular case, we had what? As the can sits on the incline, we can say that the center of gravity must be somewhere right on this dotted line, probably right about there. See? Now we have what? Weight acts down like this, and there's no distance between the line of action of that force and the fulcrum. So if there's no lever arm, there's no torque. If there's no torque, no change in rotation is possible. You'll only get a change in rotation if there's a torque. All the time or some of the time? All the time. That's what's so nice about physics. It's usually, there's the exceptions. Where are they? Whereas in chemistry, well, maybe it'll work, maybe it won't. Center of gravity in women and center of gravity in men. Baseball bats. How could you talk about the difference in the center of gravities of the two sexes in terms of a baseball bat? Okay, gang, wouldn't it be something like this? Men are generally more top-heavy. Women are generally more bottom-heavy. So when your bat is oriented like this, that's the male. There's the center of gravity. When the bat is oriented like this, there's the female, the center of gravity. And hence you find out, on the average, women have a lower center of gravity and can outperform men in those demonstrations which talk about center of gravity, leaning over, lifting up the thing, and all that sort of thing. Oh, I could talk about the pregnant woman. This is one that's loaded. I was forbidden to do this on an earlier taping of the course. There's an ordinary girl, ordinary woman. Where's her center of gravity? Right about here. And she okay?
Yeah.
Okay. Let's suppose this woman gets pregnant. Where's the center of gravity?
Just below the elephant.
Shifts forward, doesn't it? Let me exaggerate here to make my point. Okay. Where's the point of support?
Same, still there, yeah.
What's this called here, gang? Lever arm. What's this called? Force. What's the combination of force and lever arm called? What does the woman do?
Rotate.
Boom. So that's why pregnant women often have nose bleeding, bandages all over, all the time falling down, right? Yeah, it's terrible, okay? But that's not the case. Because women don't fall down and when they're pregnant. What do? Yeah, they lean back. Yeah, so what happens? So she'll stand in such a way as to lean back a little bit, pull that center of gravity back, over the feet, okay, except back pains. See the back bending to compensate? And this happens. This happens. Many women get pregnant and have bad backs as a result. So what's the solution? Yeah, wear skis. Now, if she wears skis, she won't fall over. Yeah. Or someone said backpack. All right, get a backpack. And that would work too. Let's put your arm like that. Okay. That would work too. See that? See how her center of gravity's moved back like this? But then one would say, no, as she gets more and more pregnant, she'd have to put more and more rocks in the bag. True or false? Begins with a F. HC. How come? What can she do? Move the bag back. She could have little notches on there. Instead of people saying, how far along are you? They could look at the notches and count them. Okay. Hey, let me tell you this joke about this black guy, okay? This Mexican dude and a Polish dude are in a bar, okay? This Canadian guy. Whenever you isolate one particular person, watch out, hackles go up. Or this woman. How about this man? A little kind of comfortable. Incidentally, I want to show you something in the textbook that's kind of neat. Look on page 465. See the woman? Looking at the man. But in optics, when we look at something, what do we call that something that we look at?
Object.
The object. And then we talk about object and image, right? So the lady is looking at the object. Anyone uncomfortable with that? Well, in the first edition, I had it the other way. I had the man here and the woman here.
So the woman was the object.
And the woman was the object. And whoo! Editor called up, we got to stop the presses, we got to change this. You cannot call a female an object. You can call a male an object, no problem, okay? And the hackles went up, the letters came in. Woo! But you know what? Guess how many letters have come in about this?
0.
0. Yeah. It's okay. So, whatever. So my publisher was uncomfortable with this. What they wanted to do is they wanted to have a man with a paunch. A man with a paunch. And they said, do that. Because the men aren't so sensitive to being criticized. And I don't know, my feeling is if we can't laugh at ourselves once in a while, hey, come on. You know? So whatever. Anyway, that's the pregnant lady routine, which you may or may not want to do with your school. Here's kids playing seesaw. The weight of this particular person here, the weight of this particular person here, and there's a distance here. from the line of action of that force to the fulcrum, which is a lever arm. And there's some other distance over here, call this W prime, over here. And as I told you, I was 26 years old when I was told about this. And I was really, really kind of excited about that. That all you had to do is to measure this force and multiply by that distance. See, I didn't have a notion that the world was mathematical. You know, people could talk about the shells and the everything, but it just didn't, this was just too delicious. That you could actually calculate how much weight this person would have to balance if you knew the force and the distance and you knew this distance. That this times this equals this times this. Really, that this torque equals that torque. It's kind of fantastic. The first time you're aware of that. And that it really works. And people can get out on beams and do all this. It works. Wonderful. One of the rules of nature. If there's no unbalanced torque on an object, that object will not change its rotational state. And so it's rather simple. So now we talk about here the weight times the distance, weight times the distance. And what happened if we let the fellow over here be bigger? Well, if it's a bigger guy, then he'll have to sit closer. So his heavy weight times this small distance will equal this weight times this distance. I suggest that some of us might find this so it makes sense that we might just whip right through it without really giving it credit. But I remember what it was as an adult to be told about that and what it meant to me. So I think this is worth ballyhooing about. Now, if I want to draw all the forces that are involved that act on the system of two people and a board, is my force diagram complete?
Something's going to be holding it up.
Something's going to be holding it up. And something's going to be holding it up. It's got to be a force that's like this. And we can call that the normal force. And how big is that normal force going to be equal to compared to this and this? Greater or less? Greater.
What about the board?
Because I have to take the mass of the board. And the weight of the board is in here. Call it mg. But you know what? The weight of the board doesn't contribute to torque. Because the weight of the board is right over the fulcrum. So in this particular case, I can neglect the weight of the board. I can neglect the normal force when I want to find out how closely people should sit for their given weights. And we can neglect that. But there are cases when we don't neglect it. And what about the case of a little boy, who's so obnoxious that when he goes to the park, no one wants to play seesaw with him, so he wants to be able to play with himself. How can he do that? Let's suppose he sits on the board like this. And he puts the fulcrum right here. Can that kid balance? Check your neighbor and say why it is that kid can balance. In this particular case, the kid is balancing very nicely. Let me ask you a further question. Which has more mass? The board or the boy? Or not enough information is given. Which has more mass, the board or the boy? In this case. Center of gravity is here.
You want the same? Hard to tell.
This distance is 22 centimeters. This distance is 19 centimeters. A little bit shorter. So which weighs more? The boy? How many say the boy? Let me see who you are. How many say no? Same, even though these distances are different. Stand up. Even though this distance is slightly longer than this, maybe they both have the same mass. That would be nice. Let's be fair. No? You mean if this is a longer distance, this force would have to be different than this one?
Yes.
Now, greater or less?
Less.
Yay. It turns out that concepts usually are not being taught in the ordinary engineering courses. Problem solving, yeah, but concepts not. And there's a test called the Force Concept Inventory that is now alerting people to that. Where all these conceptual questions about forces. And it turns out that students after students just fall down on them. And whatever. Here's a nice one right here. Where's this going to balance? Isn't that nice? And this is the kind of stuff we were talking about over here. And here we have 3 seesaws over here. In which case is the board and the boy equal in mass? A, B, or C? Check your neighbor. How many say A? Oh, not everybody. Oh, we have to talk about this. Well, do you guys see here now? This is certainly equal mass to this. And where is my hand? It's not the 50 centimeter mark, is it? It's right half between, right? So now I have the weight of the stick acting here. Are you guys hip to that now? The center of gravity of a meter stick, the center of gravity of this meter stick is at the 50 centimeter mark. Where's the center of gravity now? The 50 centimeter mark. Where is it now? Well, maybe not that angle, but how about this angle? The 50 centimeter mark. That's the center of gravity of the stick. Where's the center of gravity of this stick? Same place, down here.
18-inch mark.
Well, if I suspend them up here, so now what do I have? I have M here, I have M here, but mg in the middle for this one here. Whom? And mg, line of action, so it's right at the 75 centimeter mark. And there it balances. Isn't that nice? So where's the center of gravity of the system? Somewhere right in here. Right in here. Say 50, 50, whoom, right in here. Ain't that nice? In which case is the board heavier than the boy? Check your neighbor. This boy is at a big distance from the fulcrum. The center of gravity is a small distance from the fulcrum. This boy's weight times that distance will equal the weight of the board times this distance. Therefore, the weight of the board is less. You're supposed to scream and throw things. Therefore, the weight of the board is less. How many of you are going, yeah, whatever you say, Mr. Hewitt. Go back. It's more, right? Okay, so the board is heavier. Now, by logic, in which case is the board lighter than the boy? Oh, wait a minute. No, the board is lighter than that's oh, God damn. In which case is the boy heavier than the board?
The board heavier than the boy?
No, the boy heavier than the board. Getting mixed up, right? Anyway, here we have a small d. Over here we have a large d. And we know that big force times small d will be equal to large force times, whoops.
Work done equals work done.
Yeah, work's the same.
Just kidding.
I know you're kidding. And let's look at this, gang. When we talk about things like this. Points of confusion. Torques, we're all set on this, right? More torque, longer lever arm, and the angle. And you can get into all kinds of trigonometry if you want to teach trigonometry. Remember we talked about this? This is a sheet I didn't show you. This is in the energy chapter. Here we have force distance equals force distance. Here we have force distance equals force distance. Here we talked about work. Here we talk about torque. What is going on? See, I have the force and the distance in the same direction. What concept is that? Work. But it turns out that how big that d is compared to how big that d is proportional. So it turns out you have some other d prime here, and over here you have some d prime here. So you could talk about the same problem in terms of that force times that distance. This distance will equal this force times that distance. When you're doing that, you're talking about torques. When you talk about the displacement in the direction of the force, then you're talking about work. So here's a point of confusion in your instruction. And I wonder how many beginning instructors get messed up there when a student asks that question. If you really want your students to learn physics, you should have them memorize these equations. And then see how well they can remember them when you give them a closed book exam. And the one that remembers the most learns the most, right?
Right.
Begin with a W, right? Oh, it's nice to talk about predicting which will roll down inclines more based on these equations. I put these equations in the conceptual book, and I warn even the instructor, don't make the kids memorize these things. If they learn these things, they've learned nothing about physics. So, but do you be able to kind of maybe see how the M's and the R's change? You know how if you have a ball, it ought to have less rotational inertia than a solid cylinder because the edges have been cut off. You know, how much rotational inertia once something has to do with how far away is the bulk of the mass from the axis of rotation. Here, I find that this is rather easy to balance like that, but quite difficult to balance like this. Very difficult. I could pass this around. You could check for yourself. If this turns by 10 degrees, how much does the mass of the system, which is mainly in here, how much displacement occurs?
Not much.
Very little. How about 10 degrees up here? Ooh, quite a bit. This is much more lazy. And we talk about inertia, we talk about a measure of laziness. And so something is more lazy when the mass is far away from the axis than when it's close. Hence the flywheels with the great big rims. Oh, you don't see those anymore. But the great big rims with all the mass out there and the small spokes. Very, very hard to get going, but once it's going, very, very hard to stop. Has a lot of rotational inertia. So rotational inertia has to do with most of the mass times the distance. It turns out to be mass times the distance square. For my 9th graders, I don't introduce that. Oh, I guess I do when I talk about the pendulum. This has the same rotational inertia like that as it has up here. In fact, whipping in a circle, it would have exactly the same rotational inertia as a rim of the same mass and the same radius. And you can kind of look at it, things like that. Well, then you can get into this sort of thing. Knowing that's the case, this has more rotational inertia than this stick? Yes or no? Answer begins with a
Yes.
yes? Okay. If that's true, then you can tell me which of these will rotate to the floor in the shortest time. Which way, and I'll turn it like this, which will hit the board first? The empty one or the weighted one? Have you got your answer?
Yep.
Can you keep that answer a secret? Do you think I'm going to show you this? If I were a brand new teacher, all excited about my profession, what would I do as soon as what would I do? I'd show it and explain it, right? But honey, I ain't going to show it. You'll never know. You'll go all through life never knowing what really would have hit the ground first. And you know what? There's no way to know because it's not in the book, not in my book at least. So, I'm not going to show you. No. Now for $1 each, $1 each. Canadian. You've been at the mountaintops, you've been away from the city, and you've looked at the stars in the sky, looking through the Milky Way, and you're not really in a hurry and you have some time to think and no one's bugging you and no one's bothering you, you're kind of looking up and you're just kind of wigging on the stars. And how do you feel? You do get some kind of a feeling, don't you? And you start to wonder where you are and what your problems are. Your checkbook didn't balance this month, et cetera, and you look out and my God, look at it. There's the whole cosmos out there. Well, the part that you can see, not so much compared to what's there. And then you wonder if there's maybe some pattern by which all of that follows. You know, we talk about patterns, and you go to a concert, and the music might move you emotionally. You might even get tears in your eyes, and you know that really they're all looking at sheet music, and there's a pattern there. And you can go and look at that pattern, and it'll repeat it from city to city and still evoke that sort of emotion in people. There's a pattern. It's called sheet music. And then you look at the skies, and you wonder, is there a pattern that's underlying all that? Whew, well, it turns out there is. And that pattern sort of dictates where everything is and even why there's things around. And would you like to see that pattern on the board here? I will show you that. I'll show you what the pattern is. There it is, in case you wanted to know. That's the pattern that underlies the cosmos. Whoom. Not so bad, huh? Now, what's it say? It's Newton's law of gravitation. Universal law. Some people think that Newton discovered gravity. What did your textbook say about that?
Well, he invented gravity.
He invented gravity, right? He patented it too, right? Okay. Everyone falls down has to pay, right? No, sue. Okay. Yeah. No, Newton didn't discover gravity. What did Newton discover? The gravity was universal, that it extended beyond the Earth, that it extended out to the stars. In fact, it's why the stars shine. It's why the stars are round. Gravity. And what is the law of gravity? The law of gravity just says, hey, for whatever reason, there is an attractive force between everything. Everything's pulling on everything. And for every two things, one of mass this m, one of mass this m, divided by the distance square. Let me put distance to match the book. There's an attractive force. And that force is tugging on things. And as things get more and more massive, the force is greater. Here, I've got a particular planet right here. I've got another planet right here. There's a force pulling these together. What if I make one of these planets twice as massive? What does the law tell us about how much force?
Twice as much.
Twice as much. What if I make them both twice as massive? Then there's 4 times the force, see? It turns out the force is the product of the masses. How about I get them further away? Gravity get weaker or stronger?
Weaker.
Weaker. And let's suppose I get them twice as far away. 1/4. And then 3 times as far away. 1/9, etc., etc. Suppose I have a candle flame here. And that candle flame is sending light out in all directions. And let's suppose I intercept that candle flame with this eraser right here. With that eraser right here, I'm going to, looks like I'm going to catch 1, 2, 3 rays, yeah? And let's suppose that eraser is distance d away. Let's suppose I put the eraser twice as far away, say over to here, 2d. Then these rays that make a shadow back here would do this. Oh, look at this. I can get an eraser in here. I can get another one in here. And if you can think spatially, you can see there's 2 more coming out this way too. So in the shadow of that eraser, I could put 4 of them. That's interesting. 4 for twice the distance. What if I went 3 times as far away? I could get 1, 2, 3. 1, 2, 3. 3 3s are 9. And I think you can see if I were counting photons, the number of photons that hit here would spread over 4 times these. So on any one, 1/4, 1/9. What's for 4? 16th, etc., etc. So it's really some geometry as to why it is the inverse square law is as it is. And then when you plot that, of course, you get this thing like this. 1 over r squared.
You start off with your overhead projectile about 1 meter from the wall or your screen. And just look at the brightness that you get
Oh, nice, nice.
and the size of the light. Right there.
Oh.
Don't worry too much about focus, just focus together. So it's about yay big.
Yeah.
If I now come
Whoops,
to
inches.
twice the distance, what's going to happen to the patch of light on the wall? It's going to get bigger. It's going to get bigger which way? Just
That's
slightly?
strange. Twice as big.
Twice as big that way, but also twice as big that way. Yes, Dave?
I just think one thing you do too, you could divide it up into squares, and then you could have a light meter, you can show intensity, and then you add them all up, and you get
Right.
the same as the original.
That's right. Yeah,
You can
good.
even see that it's
Yeah,
not
good.
as
Yeah.
bright, but if you
Yeah.
got a light meter, the
Yeah.
portable light meter of the old cameras, and then go to three times the distance, you get 9 times the area on the wall.
Three.
So what's happened to the brightness? It's down to 1/9 because it's the same light bulb that's shining that amount of light on there. So it's a quick and dirty way to do it. And you
yeah.
can make it quantitative if you want.
The inverse square law is not appreciated by people who take flash pictures at nighttime of very, very distant things. One time, a person flying over some city, and they took some flash pictures of the city. You know, I mean, the light is going to go down, spread out, and then spread out, and have enough to, whew, I don't know. But then again, if you showed me those dishes that pick up these signals, I wouldn't believe it either. I mean, that's incredible to me. Send a beam up, comes out, and you still, I don't know. They say, what is it? Magic is any sufficiently technologically advanced civilization more than ours. Their goodies are to us magic. Oh, there's so much magic today for me. You know, the whole computer revolution and all that's going on. But, however, there are rules underneath it, and that's what we're talking about when we talk about physics. But the inverse square law is something you want to develop. And it's important because it occurs with everything that emanates from one point and spreads uniformly. Radioactivity, sound, electric fields, magnetic fields for magnetic pole. It turns out all through physics you'll find that things vary as the inverse square of the distance. As you get further and further away, the effect becomes less and less, but geometrically by the inverse square of the distance. And why that's true, you can develop and spend about 20 minutes on it, and you can develop to people's satisfaction, I think. In the text, we talk about the butter gun, shooting out butter, and the further away the toast gets, the less thick is the layer of butter. And then it turned out that people were wondering after this law, I'll read the very end of the text, kind of changed the whole politics of North America here because of Locke. Locke was so enamored with the idea that Newton had found there were regularities in nature, that nature obeyed rules, that maybe he thought there might be social rules as well. And hence the Declaration of Independence in America as a consequence of Locke's thinking. So the idea that there are reasons for things and things are connected and change one thing and another thing changes, that was a whole new way of thinking that was ushered by Newton when he developed this law and showed that this law was responsible not only for things on Earth, but all throughout. And it seemed there was only like one physics for the universe rather than the physics for the Earth and the physics for other things. And that was challenged one time when they found out the planet Uranus was going around and it was sort of wobbling in its orbit. And it seemed that little wobble might have meant that Newton's laws were breaking down. And a pair of mathematician types calculated, hey, if there's another planet out there pulling on it, it might perturb that. And they calculated where that planet might be. And the English people who made the calculation sent them into Greenwich, and the observatory at Greenwich, they opened the envelope and they said, what is this? A couple of mathematician types telling this is another planet out there. We'll throw it away. And a Frenchman, and who was it?
German astronomer.
German and a Frenchman was it? Sent it to the observatory in Paris. And they opened up the letter and they said, what's this? Someone's telling us that we'll find a new planet if we turn our telescope over and up this number of degrees. Son of a bitch. And there it was. And they found the new planet. And that's the planet what? Neptune. What's the first element after uranium? Neptunium. Yeah. And then they found further perturbations in the planet Uranus. And they found yet another planet. What do they call that planet? Pluto. And what do they call the next transuranic element? Ah, isn't that nice? The physicists and astronomers together, okay? And so that was confirmation that Newton's laws at least were working out as far as the solar system. This is not complete. You guys like to put a G in there, right? I like to introduce it like this and then put the G in later. And it turns out if you take a meter stick and hang a mass on here of known mass, and then you roll underneath it, get it so it's just, and you got an empty pan here, get it so it's just balanced. I'll put this in the middle for simplicity. It's just balanced. And now you roll underneath it 6 tons of lead of mass M. Guess what's going to happen to the distance between here and there? Take one guess. How many say gets more? Stand up. Come on. The distance is going to get more? Yeah, okay. The distance is going to get less because this is going to come down. So you know what to do to make it come down? To put it back up again? You put some little masses here. Ain't that nice? Now you measure how much mass you got there. That allows you to measure the force that the gravity was pulling. And you know the distance between here and here? Can you measure that? You can measure that. You can measure that distance. You can measure this mass. You can measure this mass. Now you can measure the force required to balance it. And obviously this wouldn't be in the middle, would it? But the idea is once you know the force, and you divide that by this mass times that mass times that distance square, you get a number. And that number turns out to be, if this is in newtons, kilograms, meters, turns out to be 6.67 times 10 to the minus 11. What happens if you use a different mass? That's like if I have the circumference of a circle and I consider it compared to its diameter. I'll get the same value if I have a small circumference with a small diameter. They'll be the same. We call that pi. We call this g. And it turns out whatever masses you use, whatever distance you use, you'll always get the same number. So we call it a constant. And right now we wonder, is it really a constant? Well, it's a constant in 1998 as far as we can tell. Hasn't been much change between 1998, 1997, or up to the year 2000 as we can project. But we have a constant there. So we can write this equation, as you see it in most textbooks, like this. In fact, they'll put an R here and an M1 and an M2. But that's that. I prefer to talk about it like this and then introduce this. Introduce the G. And what is really interesting, especially to people that live near the sea, are ocean tides. And how is it that we get ocean tides? And at this point, I ask a question that will let me know who read the book and who didn't read the book. Can I just ask this question? Is there anyone that came to class today that didn't sort of skim through the chapter on gravitation? Oh! 4 of you. Okay. How many did? Look at the hands that didn't respond. Okay. Does the moon have anything to do with ocean tides? Yes. Yeah. Okay. Which exerts the greatest force on the waters of the earth? The moon or the sun? How many say, come on, the sun is enormous. The sun, of course. The sun. Show of hands. All right, those are my people. Those are my people. Good for you. Good for you. Were there any Moonies here? Where? Oh, Teresa, you. Oh, Mona. Oh. Okay. No, it turns out there's this distinction between what force the waters are being pulled with and what difference in forces. I think we're all aware of the growing influence of the pseudosciences, the psychic network, and all that sort of thing, the horoscopes, the beliefs in astrology and whatnot. And what I've done to sort of hopefully counter that, rather than preach and rant and rave about it, everyone can do that about whatever the discipline is to go with hard figures. So look at the plug and chug, the questions that are asked. Number 1, calculate the tidal force of the moon on the earth. Number 2, calculate the tidal force of the earth on you. Guess which makes the greater tide? The earth. Then the earth stretches you. Number 4, what's the tidal force between a 1 kilogram melon on you? It's about 200 times as hard as the force of the moon on you. So it turns out, and if you want to really calculate it, take a 5-cent piece, hold it 1 meter over your head, and the gravitational pull of that 5-cent piece on your head, subtracted from the gravitational pull on your feet, is about the same as that of an overhead moon on you. So I want students to think, if they think there's a gravitational reason for the moon's influence on people, if it's a gravitational reason, then watch out for nickels and dimes that are 1 meter over your head, because they'll pull the same. And gosh, watch out for the walls and the buildings and things like that. So I think if they make the actual calculations, they might see that, maybe the other ideas aren't so solid after all. A nice way of talking about tides have to do with this practice sheet. These are just overhead transparencies, by the way, that are selected figures from the textbook. Let's suppose we have a planet that's located, say, right here. And we want to look at the tidal forces on the planet. Well, let's look at the tidal force on the part that's nearest, on the graph that comes up to here. And on the far side, it's over to here. So I have a difference in forces that is that big. And that difference in forces stretches this body out. If that same body is out here, I think you can see that the force on the near side and the force on the far side are pretty much the same. So there's a very small delta F the further away you get. So the key for tides is closeness and differences in poles. So we could say, gee, how come there's tides in the ocean and there aren't tides in the community swimming pool? Well, what part of the community swimming pool is appreciably closer to the moon than any other part? And they're all about pretty much the same distance. I'll take a cup of water and put it out in your sink and watch the moon go overhead. You don't see it come up. All parts of the water are pretty much the same distance from the moon. The fact that the top part is closer than the bottom part, that factor will give you tides. Now, is that large or small? Answer begins with a SS, small, small. And if you have something like the Earth, which is what, miles, 8,000 diameter, 8,000 miles apart, one part of the ocean to another part, to the moon, you do get that stretching, enough to lift the tides about a meter. But that's a meter out of about, what, well, miles. The Earth, the ocean's about 3 miles deep on the average, so it's not very, very much. But if you're living at the seashore, of course it is. I want to talk about satellites. Satellite motion is easy to talk about when I'm in Hawaii because most of the kids go up in the high mountain. Oh, you got the high mountain here. When you're up in the mountain, can you see the curvature of the Earth?
There's islands in the way.
Is islands in the way? Yeah, otherwise, you just take a meter stick, you hold it out, something kind of poking up here and it's down here. When you come visit me in Hawaii, we sit in my lanai. I'm only 7 stories high, but there's the banister there, and you look, it's just a tiny, tiny bit. I used to be in a 32nd story, and you could really see it there. You could see it poking up here and coming down here. The fact is, we live in a round world. Flat Earth societies, types, notwithstanding. And well, Newton talked about this, didn't he? Newton talked about if you had a cannon on the top of a mountain, and if you fired the cannonball and there were no gravity, what would happen? Go straight like this. But it doesn't because there is gravity. So the cannonball will fall beneath it. If you fire it very slow, gravity will soon pull it down. Fire it a little faster, gravity pull it down. Fire it a little faster, gravity pull it down. And watch out, sometimes you'll see depictions that go like this. Boom. Jim, your hackles just went up. Right? Those familiar with this realize that no can be, because it turns out these paths are all Keplerian ellipses, and once it makes it by here, it'll go all the way around. It's talked about in the textbook. Read it if you're not familiar with that. But the idea is the faster we fire it, the longer it stays in the air. You know. Now, Newton was able to calculate the speed of a projectile to be in Earth orbit. And the reason Newton was able to calculate that was because Newton was very intelligent. And I like to ask my students, how many people in this class think that you too can calculate with no calculator the speed of a projectile to go into Earth orbit? And I like to challenge them. I think I can get 90% of you to make the calculation in your own head, no calculator. In California, we have the Mojave Desert, very, very flat. You go in that desert, and you put up a laser, and you shine a laser beam across that desert floor. Goes out straight. But it turns out the Earth curves. And the curvature of the Earth we're on happens to curve a 5-meter drop for every 8,000 meters you go out. So if I go out this way 8,000 meters, let's call it 8 kilometers. At this point here, there would be a 5-meter drop. So that laser light would be 5 meters higher above the ground over here than it would over here. And a person out here might say, hey, you must have tilted the laser up in the air because it's further above the ground here. And you say, no, 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 no. And you put a carpenter's level on it, a little bubble in there, okay? And son of a gun, that thing is level. So the light goes straight, we say at this point, before we get to general relativity, before we get to light. It's a straight line. For practical purposes it is. But the ground turns underneath it. Okay, well that factor that we have an 8 kilometer and 5 kilometer figure here makes it nice, because now we can understand orbital motion a little bit better. Let's replace this laser with a cannon. Same cannon Newton used up on the mountain. And we're going to fire across the desert floor, and we're going to see if we can go into Earth orbit. Because certainly if we fire fast enough, we can get this to go all the way around. What that speed would be is what we're going to calculate. Well, let's just try some guesstimates. Let's try 2 kilometers per second. 2 kilometers per second. Will that go into orbit? When the space shuttle is launched, or if it's going 2 kilometers per second when it's above the atmosphere, will that keep it in orbit? Hey, wait a minute. If it's above the atmosphere, of course, it's above gravity.
Weightless, yeah.
It's weightless. That's right. There's no gravity up there. So it doesn't make any difference how fast it's going, does it? In fact, it kind of just stopped there, right? Well, they do stop there because these dishes are all pointed to one place, right? So they get up there where there's no gravity. And talk about major misconception of the public. That is a biggie in this spacefaring age. I'm convinced that there have been people in orbit who think that up there there's no gravity. 2 kilometers per second. Let's see if that'll go into orbit. And if there's no air drag and there's no gravity, 1 second later, how far downrange?
2 kilometers.
2 kilometers. Well, let's see. Here's 8, here's 4, there's 2. It would be here. 1 second later, that ball would be there, if there were no gravity and no air drag. Is that fast enough for Earth orbit? No, because during that 1 second, it would have fallen. There are people who know how far it would fall. See if you're sitting next to one of those people now. What's the answer again? Rhyme with jive. 5. All right. 5 meters down. But whoop, that's down here. But the ground's in the way. Obviously, this is not to scale, gang. But if I had dug a tunnel, a trench, then it would work. Because now my ball would have gone like that. But I'd have to dig a hole, see? So obviously, 2 kilometers per second is too slow. Let's jack it up by 2. Bring it up to 8. That would put it here at the end of 1 second. Is that right? 1 second later, it would be here. But it wouldn't really be there. 4. Oh, did I say 8? Oh, I'm getting ahead of myself. That's much. 4. 4 would bring it to here, but it wouldn't really be there. Where would it be? Still 5? It was 5 before. Still 5? Yes, it's 1 second. In 1 second, it'll go 5, so it'd be right here. So I'd have to dig a trench to keep it airborne. And I get asked, would 4 kilometers per second put it in orbit? And what's the answer? It rhymes with O. No. Very good. Okay. Let's suppose I jack it up to 6 kilometers per second. You getting the idea? Am I going too slow for you? Sure I am, but that's all right. Let's go through it. 6 kilometers per second would put it there at the end of 1 second. 6 kilometers downrange. But it's not really there. It's where? It's a 5 meter drop. Ooh, I don't have to dig as much sand out of the way. It eats less sand the faster it goes. There's a little pattern. The faster the ball goes, the less sand it has to eat to still be airborne 1 second later. Now, what would happen if I jack it up the speed to 8 kilometers per second? And at this point, I like to stop and say, how many people in this room can calculate in their head, no calculator, how fast that cannonball has to go so it doesn't eat any sand? Check your neighbor, and then we go through that. And I get 90%. Would you get 90% with your kids? And what's the answer? 8 kilometers per second will do it. Because at the end of 1 second, it's going to be 8 kilometers downrange. It's going to be just as high off the ground here as it was over here. And furthermore, it's going sideways. So there's been no work done because gravity is acting this way. Gravity is acting this way. The displacement is this way. No work, no change in energy. So you have the same speed here as you had here. And around and around and around it goes. Ain't that nice? And the calculation can be made with simple arithmetic. And then I want to leave you with this thought here. A cannonball fired horizontally. How come gravity doesn't increase the speed of the cannonball? Gravity's pulling on the cannonball all along. Why doesn't it increase the speed? But yet, gravity does increase the speed up here. If you get on top of a building and throw your keys to a friend down below, they're going to gain speed. But if you throw it in orbit, it doesn't gain speed. Because in orbit, gravity doesn't act anymore, right? No, that's not the reason. Gravity acts, but in what direction? Think about that. And then for this week's homework, is this overload, gang? 6 problems? Let me ask you a question. Did you ever give your students as many as 6 problems on a weekend? That many? More? Who said more? Oh, okay. Can you handle 6? Okay. Yes, this is ferociousness. But if you can do all 6, you'll get an A. But if you can only do 5, that's a B, and a B's fine. And if you do 4, you get a C, and we won't talk about less than 4. Less than 4 will have you stand up and give a little talk to people as to why you didn't get 4 done, okay? Well, if you get them all wrong, then we're going to tar and feather you. No, if you get them all wrong, that would tell us that you're a beginning teacher. And these are all, it's okay to get them wrong. I want you to just try them. Because if you try, if I just gave you the answers to these, blah, 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 but if you try it and you get it wrong and then I give you the answer, hey, learning takes place. The best skaters in the roller skating rink are the ones that are falling down all the time.